All right, good afternoon, everyone. So first of all, I noticed the message from campus saying that last lecture, some students are not able to find the stream. And then I found out actually that in that lecture, the video was streamed to my personal channel rather than UFU data channel. So I apologize for that. I watched the channel to which we're going to stream our lecture video, and to avoid any such kind of cases that happened before. But in case if you cannot find the streamed lecture video in the UFU data channel, you can search my name on YouTube. You get to my personal channel. There's only 2 places I can stream our lecture video to. I'll put notice on the canvas. But anyway, in whichever case, we're going to put the link of our video in our course website. So later you'll always be able to check out the lecture video. Okay, so in the last lecture, we have introduced the general framework for the variational inference. Well, we specifically call it global variational inference because today we're going to talk about another type of variational inference, which we call local variational inference. You'll see the difference later. But let us give a quick review for that because as you see, I mean, in the future, if you want to leverage some Bayesian machine learning tools in your project, your work, you always find that they follow some kind of variational, global variational inference framework. So in general, we can consider that our model consists of the latent random variable z and observed random variable x, which we often refer to as theta, right? So, and you might have some prior distribution over z, and then given z, you sample the observed variables x. So our goal is to compute the posterior distribution of z given x, which according to the Bayes rule would be dividing the joint distribution by the marginal distribution of x, right? So the k bottleneck is to compute the denominator. So because the marginal distribution, sometimes we call it model evidence, essentially is an integral. It's actually integral or marginalization of the joint distribution. So while this form seems simple, but if you instantiate with all kinds of like real world or practical models, you'll find in most of the cases you won't be able to finish this integration. And only except a few cases like Gaussian mixture model, like a conjugate, some conjugate prior plus conjugate likelihood might be possible. But in most of the cases, you won't expect you are able to solve this or calculate this accurately or exactly. So as a way to sidestep it, we need to seek for some approximation. Namely, we want to find an approximate posterior distribution of z. Well, we say it's approximately equal to p of z given x. So of course, there are a variety of ways of doing that because this is a central problem of the Bayesian model training, inference, all kinds of problems. Right? So for the variational inference, the idea is kind of straightforward. Now that I cannot compute the exact form of this, right? I just assume, okay, a simple, there's a family of simple distributions, for example, just Gaussian distribution. Assume, okay, I parameterize this approximation distribution with some known form like Gaussian distribution, so that I'm gonna find a best candidate in this approximation family, which is as close to the true posterior as possible. Right? So now, conceptually, you can view that this integration problem or marginalization problem is now turned to an optimization problem. Why? Because I want to optimize the approximate distribution to find one which is as close to the true posterior as possible. Right? That's the That's the high level idea. Right? And of course, before you do that, you need to specify what is the approximation family, right? So for the continuous random variable, a kind of very popular choice is just the Gaussian distribution. Of course, it's not, it's quite restricted, right? You can specify more flexible family of family approximate distributions like mixture of Gaussian distributions or student T distributions, or the other cutting edge research is always trying to find a very flexible, very large family of the approximations while you also do not sacrifice the computation efficiency in this optimization, right? So, and then once you have designated a family of approximate distribution, for example, Gaussian here, the remaining problem is that how do you measure the closeness between any member in this approximation family and the true posterior? Right? You have to define this before you try to find the closest one. Right? You need to tell what do you mean by closeness. Right? So again, there are a lot of candidates to measure this closeness. And in machine learning area, the most commonly used common choice is just KL divergence. So KL divergence from the approximate distribution to the true posterior. So conceptually, as long as we minimize the KL divergence from the approximate posterior in your designated family, right, to the true posterior, I just find the one who has the minimum KL divergence. Then this is my best approximation. That's the idea, right? So this is quite intuitive, but there comes out a feasibility issue, right? Because I actually don't know what is the true posterior. I don't know its true posterior. How can I calculate KL divergence between any third distribution from this from third distribution to this true posterior, right? In other words, ironically, if I can really compute this true posterior, why should I approximate? So to sidestep of this problem, we need to avoid the direct computation of KL divergence. Then we're going to leverage a very well-known trick, right? That comes from the EM algorithm. That is the decomposition of the log model evidence based on Jensen's inequality. Right? We have introduced this structure during the discussion of the EM algorithm. Right? So by applying the Jensen's inequality, it is pretty easy to show that the log marginal distribution of observed data, which is also referred to as log evidence, can be written as a summation of this lower bound plus the KL divergence. Okay. So, and this lower bound essentially, you can see that as an integral, right? Inside the integral, we're just multiplying your approximate posterior Q of z times log fraction between the joint distribution and the approximation. Or in more concisely, you can write it as an expectation. Right? Expectation under Q of z of this log fraction. Okay? This is the definition of expectation. Okay? So we refer to this as a variational model evidence lower bound in that the KL divergence is always non-negative. Okay? So meaning that this is indeed a lower bound. It is always less than or equal to this true model evidence. Okay? And if we assume, okay, there's not any other hyperparameters, the model evidence is there, it's constant, right? So you know that this fixed evidence is an addition of your evidence lower bound and the KL divergence. In other words, if you maximize the evidence lower bound, it is equivalent to minimizing this KL divergence. Right? So the larger the evidence lower bound you have, the smaller the KL divergence from the Q of z to the true posterior. Okay. So now I want to ask a question. when will your lower bound reach its maximum? Yeah, KL is 0, right? If you can find a Q of Z, which makes your carrier divergence to be 0, that means your Q of Z is exactly the true posterior, right? And of course, because you restrict the family of the Q of Z, you actually limit the range on which you optimize. Okay? So that means your carrier divergence will always be non-zero. Of course, I mean, theoretically, if you don't put any constraint of the Q of Z, you assume Q of Z is just a free form. It can be whatever you want. And theoretically speaking, you maximize this vertical lower bound. It is very easy to show that your Q of Z exactly P of Z given X. But in practice, you always have to find a trade-off. In practice, it turns out that the larger the family of Q of Z you choose, the more difficult to maximize this evidence lower bound. And in an extreme case, if you don't put any constraint, in other words, you assume Q of Z belongs to the whole family of possible distributions. Although in theory, you can reach the true posterior, but in practice, you will never be able to compute that or arrive at that. Okay, so, and then given this framework, the remaining thing, I mean, in practice, is to define the family approximations of Q of Z, right? And then, given your family of approximations, you try to maximize the evidence lower bound to find optimal approximations in your designated approximation family. That's the whole framework. But there's a lot of tricks about how to smartly defining the range of the approximation family and how to smartly optimize this variational lower bound. Nearly each new variation learning algorithm is just about how to play the tricks, like how to define Q of Z, how to efficiently optimize this or maximize this lower bound. And then we introduce a very classical and popular type of variational approximations, which we call mean field variation inference. So mean field variation inference do not give a parametric form of your approximate posterior Q of Z. Instead, it assumes some like structure in this Q of Z. Namely, I assume this approximate posterior can be factorized over subgroups of variables inside Z or individual variables inside Z. How to factorize is totally up to the user. You can make a stronger assumption that, okay, I'm gonna factorize Q of Z individually, or I can group those variables beforehand and I believe they should factorize over each subgroups. So, but for each factor, right, the Q of Zi, you don't need to specify the explicit form for that. Then the question is that if we put this factorization structure in my approximate posterior, how should I efficiently optimize Q of Z? So we introduced the so-called mean field variation inference algorithm, which is essentially a coordinate updating or alternating updating scheme. So every time we just fix one factor, Q of Zg, while fixing all the other factors. And it's not very hard. It's relatively easy, but you need to spend a few steps to show that if you fix all the other factors and if you want to find the optimal Q of Zg, what we need to do is that, okay, I just take a logarithm of my joint probability, and then I take expectation of my log joint probability under the current Q of Z not G. Z not G includes all the other variables excluding ZG. So you can view that after taking expectation, this whole guy becomes a function of ZG, right? Because all the other variables have been marginalized out. We're doing expectation, right? So, and then you take EXP again, because then you can ensure that EXP of this F of ZG is non-negative, right? And you can do the normalization, and then that's your optimal Z of G, Q of ZG, given all the other factors are fixed. So I'm not going to repeat how we show that. I hope that after class, you guys have tried to redo the proof or follow the proof we did together in the last class. Right? But it's really not hard thing, but it's good for you to understand how this is how this is derived. Right? So, and then this is the whole mean field variation inference procedure. Right? So essentially, inside each iteration, we just cyclically go through each factor. Right? For each factor G, we're going to fix all the other factors, and after update Q of ZG according to this formula. Right? And then we move to the next factor, and we fix all the other factors and update the corresponding factor following this formula again, until you finish the updating of all the factors in this iteration. Then this iteration is done. We move to the next iteration. We do this again and again until each factor doesn't change much. I mean, less than some designated tolerance level, or you have reached maximum number of iterations. This is a typical alternating update scheme. So we have showcased in this variation linear regression how we conduct this mean field update. Right? So I'm not going to repeat this, but again, highly recommend everyone to try to derive these updates. Actually, in most cases, you will not need to really do the normalization by yourself. Like we know we need to take EXP and do the normalization, right? But actually, in most cases, when you take logarithm, you take expectation, you take EXP, it will give you some like a standard, some k terms in some standard distributions. From that, you will know that it corresponds to what distribution. So you don't need to really calculate normalization factor. And to get detailed sense about why we're doing this, please practice this example. Okay, so now we want to introduce a more general mean field variational updates in the so-called exponential family. Why we emphasize exponential family, because it's so important. Many easy to deal with distributions are inside this framework. So once you know this general framework, you can simply instantiate for the detailed distributions. So here we assume our model, of course, is hierarchical model. So you got some latent random variable eta and latent random variable z, and then the random variable x. So in general, we assume that given eta, the joint distribution of your observed data x and z is represented by some exponential family distribution, which in general gives you this form. Right? So if we still have an impression about this form, the exponential family distribution of exponential family can be written as a kind of like a independent factor of the random variable x and zn times this is an exponential form. Right? You can view this guy as like some independent term, and this has nothing to do with exponential part. This is just to account for all possible other factors other than the exponential term, right? So the k term we are interested in is here. So we got exponential, and the power has a linear structure. which is an inner product between the natural parameter eta and the sufficient statistics u, right? So sufficient statistics summarize the information of this inside these random variables. So usually we use this is a mapping, right? From the random variables x and zn to the sufficient statistics. So it's an inner product eta transpose u x and yn, and g eta corresponds to the normalization thing, right? Remember when we talk about exponential family, we sometimes written something like this, right? Like lambda, something like that, right? This is just to ensure that this guy is kind of log normalizer. So here we just put g of eta outside that, but you have to make sure that g eta is equal to right, just to ensure that the whole integral of this density is 1. Right? So that's why sometimes we call it partition function, but here it's just the inverse of partition function because we didn't put it on the denominator. And I also show that, and here we choose the convenient for that the prior of the natural parameter is conjugate to the likelihood. Right? This is the general form of the conjugate prior to the exponential family likelihood, which we have discussed before. Right? So you have this factor, and this guy can be viewed as some term in charge of the normalization. Right? And g of eta to the power of nu 0, which we call it a degree of freedom. Right? And exp to the power of nu 0, and eta transpose this kappa 0, right? Kappa 0 and nu 0 are just hyperparameters. Okay? So now once we have defined this joint distribution regarding natural parameter eta and the likelihood of z and x, suppose our task is to compute the posterior distribution of eta and z given observed data x. How can we do that? And even you see that even as a conjugate prior to the likelihood, you're still not able to compute the exact posterior here. So we need to seek for some approximation. Here we apply the mean field variation inference again. Right? So that is, we assume q of z and eta, these two random variables we're interested in, has this factorization structure. Right? We assume it is q of z times q of eta. In other words, we assume in our approximation, z and eta are independent in the posterior. Okay. And then next thing is how can we update q of z and q of eta, right? Following the mean field variation inference, we know that the framework will be okay given q of z, update q of eta, and then given q of eta, update q of z, right? It's just to do this in an alternating way until convergence or maximum number of iterations have finished. Does it make sense? Right. So let us do this together, right? Let us do this together. Get another concrete practice of doing mean field variation inference. Okay? So let us try to update q of zn first. Right? So that means we assume we're going to fix the current q of eta. How do we update q of zn? Following the updating rule we have previously derived, right? So we're going to take logarithm of the joint distribution, right? So logarithm joint distribution will be p of eta plus logarithm. Remember, this is a likelihood over n points, right? And the likelihood that relates to zn just contains this guy. Right? So all the other n doesn't contain Zn, so you can just throw them out. So you can just look at logarithm of P of xn, Zn, given eta. Okay. And then you take expectation under Q eta for this, and then take exp for this. Right? Does it make sense? Oh, the number of data points. Yeah. Because like you imagine that, okay, I have observed 1,000 examples, right? That's n, big N will be 1,000 examples. And the Zn is just for one particular example, like a 10th example or 9th example. And the question, I assume everyone feels comfortable right now. Okay. So then let us look at, because finally, we just want to get a function related to Zn only, right? All the other terms which do not include Zn, they are actually constant. Right? You can just throw them out. It's not necessary to be included because even you include them, it is constant to Zn. You take expectation, then you do a normalization, just cancel it out. So actually, you only need to look at in the log joint probability which terms really involve Zn. And it turns out that the log prior doesn't involve Zn at all, right? So they're constant to Zn. They're going to be canceled out when we do the normalization. So don't need to care about that. So the only term that care about or includes Zn will be the likelihood of x and Zn given eta, right? Which is this guy. Okay. If we take the logarithm, so let me write it down in a more clear way, right? To eta here. So you just throw them out. You only have this log p xn Zn given eta. That needs to be carried, right? All the other things, it's just the constant. Right? Because they have nothing to do with Zn. Okay? So now you just need to take a logarithm. This is a log p of xn Zn given eta, right? So if you take a look at this, it's log h xn Zn plus log g of eta. Remember, g of eta has nothing to do with Zn as well. So it's constant, you don't need to care about that. And then you only need the eta transpose u xn Zn, right? And other things, again, is constant. Right? So now if you take expectation over this, and log h xn Zn doesn't contain eta, so your expectation is still itself. Then what you need to do is just take expectation here. So that means after the range of this term is pretty easy. Just exp logarithm of this h xn Zn plus the expectation of eta, right? Transpose your sufficient statistics. Right? This is your updated Q of eta. Oh, sorry, Q of Zn. And this, if you take exp, of course, it's still an exponential family distribution, right? And remember now, natural parameters becomes the expectation of eta, right? And we know that the normalizer factor is a function of natural parameters. Now the natural parameters becomes the expectation of eta. So that means your normalization now becomes g of expectation of eta. And that's it. Any questions so far? Okay, so let us do another example. I just don't want to make the whole framework too abstracted so that we can get as much concrete experience as possible, so that when you implement some particular model by yourself or doing some practice and homework, you won't feel like you won't feel like scared about that. It's really some kind of like mathematical simplification and throughout terms and those kind of games. So now let us try to update the Q of eta. Okay. So that means we're gonna fix Q of Zn, right? All of Q of Zn. Remember, we have a big N Q of Zns. Okay. So if we update Q of eta, which is the same updating formula, again, we're gonna take exponential. Inside this exponential, we're gonna do the expectation of Q. Now it's under Z, right? And then the logarithm of P eta was prior here, plus logarithm of P x Z given eta, right? But now you can now throw out the log prior because the log prior directly involve eta, right? It is directly related to eta. You need to preserve that. Right? So sorry. And then we can just do some kind of tedious logarithm, right? So first, again, for any terms inside the prior, which is constant eta, you can just throw them out. This doesn't change the result. So you can just look at the terms which contain eta, which that will include g of eta to the power nu 0 and this exponential term. So take a logarithm, it will give you nu 0 logarithm g of eta plus nu 0 eta transpose kappa 0, right? And then you take a logarithm over this likelihood. Of course, you need to do the summation, right? Summation over each data points. And then again, if you look at this likelihood, you can just throw out any terms that has nothing to do with eta, right? So this guy has nothing to do with eta. You can just throw them out. Just take a logarithm of all the terms that contain eta, right? So we got logarithm of g eta plus eta transpose x n to n. Okay. And remember, we need to take expectation of this log, drawing probability under Q of Z. So here, the only terms that involve Z is here, the sufficient statistics. All the other terms are constant to Zn. So that means when you take expectation, you just replace the sufficient statistics by their expectation. It's going to be E Q of Zn. And then you just merge the terms, right? So you can see that your power in this EXP is actually has two terms. Right? Sorry, it's now first term is regarding log g of eta. You can see there nu 0 plus n, big N. Yeah, big N log g of eta, right?
It's not visible.
What?
You cannot see what's going
on.
The screen. The problem is.
Oh, okay. This is a screen problem. Okay. Too bad. Okay. Let me put it here, right? If we merge the coefficients of log g of eta, is simply nu 0 plus n. Okay. And then if you look at the coefficient of eta itself, it is let me put it here, is eta transpose in nu 0 kappa 0, it's here, plus and the summation goes through each data points, then you take the expectation of each sufficient statistics. And then if you take exponential, it will give you the same form of the prior, but the parameters is changed. Right? So here is the update. Right? So if we denote it by nu n and the kappa n, you see nu n is the nu 0 plus n, which is the coefficient of our log g of eta. And for kappa n is the nu 0 x 0 plus the summation of the expectation of sufficient statistics. It's just the term we have merged for eta. So this is pretty easy if you want to sit down for 5 minutes to merge all those terms. It's not hard at all. And then you can do this alternating update. Right? You fix q of the n, you update q of eta, and then you fix q of eta, you update q of the n until these alternating updates converge or maximum number of updates I'm done. So this is a kind of like general mean field variation inference framework. If your model falls into this category where you have a conjugate prior of the latent random variable eta, and then this z and this latent random variable z and the likelihood x is a member of the exponential family distribution. So actually, the variational linear regression falls into this form. We can use this general update form to instantiate this variational linear regression model as well, if you want. Okay, so far we have finished the introduction of global variational inference. Any question? Where everyone has fully captured the whole idea, right? And now, as to some specific problems, well, you have to define your own approximation family. You have to develop your own optimization algorithm to maximize that lower bound. Okay, so now let us look at the local variational inference. So, what is local variational inference? It is directly works on the joint probability. So if you have a z of x, so p of z and x, and suppose we're now trying to directly introduce a variational posterior for that. Instead, we want to make this whole distribution easier to be dealt with, easy to deal with. Right? For example, suppose we have this structure, right? We know that the reason we can't compute the posterior distribution of z given x is because the combination of the factors in this distribution make the whole marginalization intractable, right? So another idea is that, okay, why not I try to simplify the factors in my joint distribution? Like if I can derive some relaxed form of any factor, any annoying factors in my joint distribution, and by using that relaxed form, I can analytically or very easily obtain some kind of approximate posterior. That is the idea of local variational inference. Okay. So, and how can we get some relaxed form for some factors in my joint distribution? The most commonly used tool to get such kind of relaxed form is the convex conjugate. That's something we have discussed before, right? We mentioned that this will be very useful, and now we'll see why it is useful. Right? So here is just a quick review of the convex conjugate. Right? So suppose f is a convex function, and we can always construct a lower bound of the convex function. This is a convex function, and of course, according to the convex conjugate, we can construct a lower bound by maximizing this linear function to x. So lambda of x subtracted g of lambda. We have we actually have showing that this, the right hand side essentially is a tangent line at the corresponding x. So this is your maximum lambda x subtracted by g of lambda. Oops. Oops. One second. All right. Maybe there's this contact. I mean, this is connection of these lines. Lose a little bit. Okay. So, so for any x, this lower bound is the lambda is it essentially gives the slope of the tangent line which passes x. Okay? And you can see that it is a lower bound because the whole function body stays above this this tangent line. Okay? And as to how do you get this g of lambda, you can obtain g of lambda by maximizing another function, which is lambda of x subtracted by f of x with respect to x. You get g of lambda. Okay? So we get some like interesting graphical illustration of this. We're not going to repeat this, but just to give you the form. So from this, we can observe that if one factor in my joint distribution is convex, then I can construct a convex conjugate, which is a lower bound, to replace that factor, like p of xn, the n, if it turns out to be convex to, this is a function of the n, right? If it turns out to be convex to the n, I can just replace it by a lower bound, right? Convex conjugate, which can be like lambda n, the n subtracted g of lambda n, right? So the benefit is that once I replace the original factor by its lower bound, now relate to Zn, it becomes a linear term. And usually, we shove a linear term inside a joint distribution, it becomes a lot easier to deal with. That's the idea. Right? But someone asked, well, so what's the rationality? I can shove my original factor. I can replace my original factor by a convex conjugate. Right? Because we know that there's choices of lambda which can make my lower bound equal to the true factor. Right? So what I need to do is just maximize this lower bound with respect to lambda n to find the optimal lambda n which reaches the original factor value. So in this way, you can view like, okay, I kind of introduce a transformation of the factor, of the original factor. And in its transform form, this transformation, the form is much easier. Then my remaining task is to find the best additional parameter lambda n here to make my relaxed form to be the same as the original form, or at least as close to the original form as possible. That's a high-level idea. Does it make sense? But I have to tell you, in practice, I mean, although in theory, you can replace any factor if this factor is convex by its convex conjugate, and you associate each input with an additional parameter lambda, which this lambda is often called variational parameter because you introduce an additional parameter, right? And although in theory you can maximize this convex conjugate, namely their lower bound, to ensure that the optimal choice of lambda will make your lower bound exactly the same as the original factor. In practice, because for convenience, for computational efficiency, you have to make some constraint on lambda. So it won't guarantee your lower bound, right-hand side, will reach exactly the same the original factor value. That means there is always some gap between this lower bound and original joint distribution. This is very similar to the global variation inference, right? You restrict your approximate posterior into some simple family of distributions like Gaussian, like student T, right? So although you simplify the computation, the price is that there is always a gap between your approximate posterior and your true posterior. So here comes the same result. You'll find that although in theory, if you don't put any restriction on those additional variational parameters lambdas, you can recover the exact joint distribution for sure. But to save computation, to make a computation feasible, you always have to sacrifice the flexibility of lambda. You have to put some constraint on lambda. You have to simplify the range of lambda. In that case, although you still can optimize lambda in some smaller range, you'll not be able to reach the real optimal values that ensure you recover the original distribution and factors. Does it make sense? Okay, so let us look at some example, right? So if we have a joint distribution over a random variable theta and the observed data x, so in general, we have some structure, the log joint probability can be decomposed as log prior plus the summation over the data points. That is log likelihood. For example, if your log likelihood is convex to theta, you can apply the convex conjugate. You replace the log likelihood by its lower bound with respect to lambda, right? And then you can maximize this lower bound. You can try to calculate Q of theta based on this lower bound of the log joint probability, and then you maximize the lambda values. Right? So now let us try to use this kind of idea to get easy inference for the logistic regression model. Right? As we mentioned before, the logistic regression, if you directly compute the posterior, right? So suppose this is your prior of the weight, right? And suppose y is your label, y is either 0 or 1, right? So your likelihood is actually the sigmoid function of W transpose. Then let me write it as phi n, because you might do some nonlinear transformation of the feature. 1 minus 1, 1 minus 1. So this is a Bernoulli likelihood, where the parameter, the probability of the Bernoulli likelihood is a sigmoid function of the prediction score. Right? So if you calculate posterior distribution of W given Y, you'll find that it is analytically intractable. It doesn't have any analytical form. Right? So naturally, we would like to consider if this likelihood is convex. Right? If this likelihood is convex, and we can convex to W, then we might be able to replace the likelihood directly by a linear form of W. Right? That's the convex conjugate, the lower bound. Right? But unfortunately, in this case, if you look at log sigmoid function, it is not convex, it is concave. And why it is concave, I will leave it as exercise for you. But you should leverage the property that the derivative of sigmoid is sigmoid times 1 minus sigmoid. If you leverage this property, it will be very easy to show that the second derivative of log sigmoid over dx squared will always be less than or equal to 0. That's where you can show, from which you can show that the log sigma function is actually concave, not convex. That means you cannot directly use the convex conjugate. So, and how can we step this problem? So we need to do some like smart rearrangement of those terms. So now that log sigma x is concave, we cannot directly operate on log sigma x. Let us look at if we can find a part of this log sigma x for which it is convex, and we can construct some convex lower bound. Right? So if we look at log sigma x, its log is 1 over this guy, right? We just move -1 to the front. It is minus log 1 plus e to the power of minus x. If we take the common term, e to the power of minus half x, and this log, because log is just log product, the sum of log, right? So we can move this term outside. We get half x subtracted by logarithm e to the power of half x plus e to the power of minus half x. So you can see that the log sigma x is some linear term of x subtracted plus this f of x, right? So because the linear term is always easy to deal with. So if we can show some convex property related to f of x, we can still construct a lower bound, right, by using convex conjugate. And unfortunately, you still cannot show f of x is convex to x. But the good thing is that f is convex to x squared. That's a very smart observation from our pioneer machine learning researchers. I don't know. I cannot imagine if I were them how I made such kind of observations. But let us just give the fact. Right? So basically, if you look at f of x, it is minus logarithm e to the power of half x plus e to the power of minus half x. Right? So first, you can see that f of x is symmetric, right? Sorry. Let me share again. Maybe I need to switch to another. So it's symmetric. So that means you can also view f of x is a function of x squared. So you can view f of x is g of y, or not g. Let me use h of y, where y is x squared. Right? So it is essentially equals to f square root of y, right? Because f of x equals to f absolute value of x. Right? No matter x is bigger than 0 or negative than 0, to give the same results. This, due to this symmetry, right? So if you will this form as a function of x squared, or in other words, h of y is equal to f square root of y, then it is relatively easy to show that h is convex to y. So in other words, f is convex to x squared. And you can verify this by yourself. The computation is a little bit tedious, but it's not hard. It's just a manual verification, nothing else. I did this many years ago, quite a few times. So I was quite familiar with this framework when I was first starting my PhD program. But anyway, This is a very good observation, a very good observation. So that means I can will f or is a function of x squared, then I can immediately construct a convex conjugate. So if you feel it's comfortable, it's uncomfortable, you can first will it as a maximization. Remember, if you want to take if you want to define y as x squared, then y must be non-negative, right? So this guy is lambda y subtracted by f squared. Now you just replace y by x squared. You get this form. So don't feel uncomfortable like that. Any questions so far? Okay. So now let us try to obtain this g of lambda. Because if we want to construct a lower bound of f of x, right? F of x, we know that it's bigger than or equal to lambda squared subtracted by g of lambda. Right? We need to know the form of g of lambda. Right? The g of lambda is obtained by solving this. Right? So now we want to maximize this lambda x squared subtracted by f square root of x as x squared with respect to x squared. Right? That means you want to take let me look at this guy. Right? So if you write down as h of h of x squared, right? You want to solve the gradient to be 0. Okay? And remember, here we assume input is x squared, not x. It's a function of x squared. So don't get confused. You need to take the derivative with respect to x squared. And and how can we get this derivative? We just use chain rule. Because dx squared over dx squared equals to or dx times dx over dx squared. Okay, just a chain rule. And this guy is what? What's this? Yeah, 1 over dx squared over x, right? Just do this to x. Okay. And then what you do is just the most comfortable setting we have we used to do, right? Just to will this whole function as x, and then you take derivative with respect to x, and after some kind of manipulation, you get the gradient to be this form. So it's lambda plus 1 over 4x tan h half of x. So the definition of tan h is not like a triangular function. Don't get confused. Tan h is just here. Tan h is here. So it's e to the power of minus x subtracted by e to the power of minus x divided by their summation. This is tan h. It's not tan. It's not tangent. Okay. So this is consistent with of fx because look, this is definition of fx. They're all related to e to the power of x and minus x. So it's not surprising that you get some formula of tan that includes tan of h, tan h of x. Okay, so and now if you give any lambda, if you want to find the optimal x squared to get g of lambda, you just solve this equation related to solve this equation according to lambda, right? And let us denote the optimal x, which corresponds to lambda, by c. Okay? And from this equation, we know that the optimal x must satisfy this equation with lambda, right? That means lambda is equal to minus 1 over 4 epsilon tan h half of epsilon, right? And of course, you can see that there's actually a mapping between, it's not epsilon, sorry, mapping between c, the optimal x, and lambda, right? You can feel like given lambda, we know what is optimal x, which is c, or given c, we know what is the corresponding lambda. Okay. And if you do some kind of like further simplification, you can also say this lambda c can be, this is just to operate terms on tan h, you got this minus half 2 qc sigma qc subtracted by half. Our observation is that if you look at the mapping between qc and lambda, it's actually symmetric because qc and minus qc correspond to the same lambda. This is the reason. I mean, it's very easy to test this symmetry here, but conceptually, because qc and minus qc correspond to the same x squared, right? Correspond to the same qc squared. You're solving with respect to x squared. So this naturally, like same x squared may correspond to different x. Right? One is positive, one is negative. This is natural. So again, don't get uncomfortable here. There's nothing to feel upset. Okay, so any questions so far? I believe everyone. It looks like everyone is comfortable here. Okay, so now once we have obtained g of lambda, right? Let us assume we know qc. Right? We're not explicitly solve qc, right? We just know qc. Right? Why we don't solve qc according to lambda? Namely, we represent qc in terms of lambda. It's just for convenience. We don't solve that because later you'll find that you actually don't need to do that at all. All things are canceled. Okay, let us assume we know this qc, right? We know there's a relationship between lambda and its corresponding qc, and we can write down our g of lambda as this linear function. Right? Remember, g of lambda is maximum of this guy, and the optimal x squared is qc squared. So you shove in the optimal x squared, you got the value of g of lambda. So this is a lambda qc times qc squared subtracted by f qc, right? So f qc, according to the definition, will be minus logarithm e to the power of half qc plus e to the power of minus half qc minus you got positive. That's the form of g of lambda. Okay. So now we can use the convex conjugate definition. Right? Remember, fx is a convex to x squared, so it's a convex conjugate. Lower bound is lambda x squared subtracted by g of lambda. You just replace g of lambda by this form. Right? You get f of x. The lower bound of f of x has this following form: lambda x squared subtracted by lambda c squared subtracted by this logarithm. Right? So, and remember, our goal is to get a lower bound of log sigma function. From our derivation a minute ago, we knew log sigma x is half x plus this f of x. Right? You just shove this lower bound of x in, then you take exponential, you get a lower bound of your sigma function. You see that in this lower bound, I mean, this is pretty straightforward. If you spend like 30 seconds to derive that, you get this form. Okay? So it is lower bounded by sigma of qc exp to the power of this half x difference between x and qc, and plus this lambda and x squared subtract by qc squared. So now I want to ask, what's the benefit of this term? The lower bound. And remember, x is some kind of random variable we're interested in, right? If you put some sigma transformation of x and you couple sigma x with any other prior, it's very hard to calculate normalization and do the posterior, to calculate posterior, right? Now, if you deal with lower bound, you see that first, the annoying sigma stuff is only applied to the qc, right? This additional parameter, right? And the terms related to x is just Gaussian terms, right? So this is the exp of a linear term to x and the linear term to x squared. It highly resembles like Gaussian distribution terms, right? So you can imagine if your x is some Gaussian-like distribution, when you merge them together, you know, exponential times exponential, you just merge all the first order term and the second order term, you get a Gaussian-like posterior. This makes things a lot easier. The price is that, okay, I'm going to introduce an additional variational parameter to C and put some nonlinear transformation over to C. And of course, to tighten this bond, I need to maximize, I need to find optimal to C to tighten this bond. And here's just the one example to show if you pick up any particular C, what is corresponding lower bound? And remember, C and minus C correspond to the same lambda. That's why there are two places where your lower bound reaches the same value as the original factor. And this first, this is not convex function, right? So you can assume like there you have some line here because this is a log sigma x subtracted to half x is convex to x squared. Right? You have a bunch of nonlinear transformations to get this lower bound. That's why you didn't see some nice like linear form on that. After several nonlinear transformations, that's why you get this looks like banded lower bound. Okay. So now let us look at the likelihood of a logistic regression. Right? So suppose this is our feature vector phi, right? And we have a binary output t. Right? T is either 0 or 1. Then the likelihood of t given w is this Bernoulli likelihood. Right? And the probability of the Bernoulli is a sigmoid function of the score. The score A is the inner product between the weight vector w and the feature vector phi. Okay? So if you just substitute this w transpose phi for A in our likelihood and then merge the terms, you get your likelihood has this following form. That is e to the power of at. Again, A is w transpose phi, and sigmoid to the sigmoid of minus A. And remember, we got our lower bound of sigmoid function just a minute ago, right? So now, from the previous results, we can construct a variational lower bound of sigmoid function for any input value z, right? Which has this form. And here we so previously we write it as a lambda c, and lambda c is minus, right? So here, just for convenience, we put minus sign here. So lambda, in the lambda, we just get rid of this front minus sign. So this is just for notation convenience. Right? So now we just substitute this lower bound into the likelihood. So we know that P of T of given W, this likelihood is e to the power of AT, this sigmoid function, right? You just apply this lower bound, you replace Z by minus A, you get this lower bound. Okay. So now we know that for each particular observed binary response, the likelihood has a lower bound, e to the power of AT and sigmoid of the C and exp to this power minus A plus C over 2 subtracted by lambda C A squared subtracted by C squared. It seems a little bit tedious, but the structure, as we mentioned before, is very nice, actually. So now, if you look at the joint distribution, right? Suppose we have a n data points. And each data point, we have a likelihood P of t and given W. And we have a Gaussian prior P of W, right? And if we want to compute the marginal likelihood, we just need to marginalize W, which is infeasible. But if we lower bound the likelihood, each likelihood term in the joint distribution by the variation lower bound, we just right? We construct a much easier form to deal with. Right? So here is the lower bound of each likelihood. When you multiply together, for each particular data point, we introduce a additional variational parameter per se n. Right? So if we multiply them together, you just multiply a bunch of sigmoid function per se n and the ESP term. And here, this guy just A, right? AN, and this guy just A. Just to substantiate, instantiate A by the form. You can see that in this exponential term, they're all Gaussian-like regarding W, right? Does it make sense? Right? So if you W is Gaussian, right? Some mean M and sigma, right? If you do the exponential, it's just it's just something like W transpose, sigma inverse W, right? It's quadratic term, right? And some linear term W transpose A, something like that, right? So if you substitute W into our variation lower bound, you see that in this lower bound, the form is kind of same, similar, very similar. So that means if you merge the prior with the lower bound together, it is very easy to compute the posterior distribution. Of course, this posterior distribution is not exact posterior distribution because you're computing based on lower bound. Right? So we know that in this case, for the variational logistic regression, if you want to maximize this expected log fractional, which is lower bound of the true model evidence, it is infeasible because the joint distribution is P of W times a bunch of sigmoid likelihood, right? So even you maximize this guy, it's not feasible, right? And if you don't put any restriction on over Q of W, maximizing this lower bound, evidence lower bound is equivalent to minimizing this, the KL divergence from the Q of W to the true posterior. And of course, if you're able to do that, you're essentially compute the exact posterior. Okay? But unfortunately, we're not able to do that because this intractability introduced by the logistic likelihood. So our goal is that, okay, we're going to introduce the lower bound of the joint probability, which is P of W times this H of W per C, right? We introduce additional parameter per C. Then we shove this lower bound into this expectation. Okay? Then we maximize it with respect to Q of W. And turns out that, as we just mentioned before, right? We will shove this Gaussian-like term related to W plus multiply with P of W into our expected log fraction, right? When you maximize this Q of W, you actually don't need to do any gradient-based optimization. It gives you the optimal Q of W, which is Gaussian. Right? So you can directly compute it. It's a Gaussian distribution, and by using the square completion trick, you immediately get what is the mean, what is covariance for this Q of W, which maximizes this expected log fraction. But this is not done, right? Because we need to ensure this QC, the choice of QC, which can make this lower bound to be as close to the true joint distribution as possible. So we got another step. That is, we maximize this lower bound with respect to C. Okay. So once given C, we can calculate the Q of W, which directly maximize this objective or expected log fractional. And then we fix Q of W, we maximize this expected fractional with respect to C to ensure that my lower bound is getting closer and closer to the true joint distribution. That's the idea. So now you can see this is like alternating of this again. Right? We're gonna fix C, then we optimize Q of W, which is analytical, which has closed form, which is Gaussian. Right? Then we fix Q of W, we maximize this lower bound with respect to C to make it as close to the true joint distribution as possible. And we maximize with respect to C, you see why we don't directly solve C in terms of lambda, because when you take the gradient of this guy, you see that you actually never need to care about lambda at all. Your optimal C is directly solved, has this form. And of course, this form is determined not only by the data, the input feature vector, but also by the current expectation of WW transpose, which is from Q of W. That's the whole procedure. So essentially, this is doing an EM procedure. Okay. So we got variational parameters to see as our, well, it is not correct to say it's a hyperparameter of the model. It's just an additional or auxiliary parameters introduced to make an approximation. But we never need to treat it as a random variable, right? We just need some point estimation. So given this additional auxiliary parameters to see, when we optimize Q of W, it is very easy. It is equivalent to the E step. You just calculate the optimal Q of W in the closed form. And then you fix Q of W, you maximize this lower bound with respect to C, which is corresponding to M step. So just to conduct this E step and M step, E step, and M step until, convergence or the maximum number of iterations I'm done. So it's kind of same framework as in the EM algorithm. But the idea, but the concept of this Q of W and C is different from the EM, right? The EM, this Q of W is too posterior under the hyperparameter. But right now it's not, because your lower bound, your maximizing, is actually now corresponds to the lower bound computed based on the true joint distribution. You just replace the joint distribution by its lower bound. And when you maximize this auxiliary parameters Kc, this Kc is just introduced to relax the form of the joint distribution. It's not some model hyperparameters. There are some conceptual difference, although the computation steps are kind of like very similar to each other. Does it make sense? So, okay, I think that's all about today. Variational logistic regression, and it's kind of like a good and a classical application of the local variational inference for this popular models, and works pretty well. I got a lot of experience using this method to do the Bayesian inference for the logistic regression models. But later we will talk about nowadays you don't need to apply this trick, and you can use other stochastic optimization method to directly optimize the variational world. But we'll talk about that later. Okay, see you on Thursday.